So now in this lecture, Advanced Strength of Materials, we'll cover lecture number 2. And I'm going to cover the idea of stress, tractions, and equilibrium equations. That's what we'll be covering today. And as I discussed in the previous lecture, the why we care about this topic of stress, we care because that's one way. If you can predict stress in the body of material of interest, like say an airplane, I'll keep using airplane because that's what I've worked: rockets, launch vehicles, spacecraft. I've also worked on some automotive applications, but I would choose an aircraft, right? But it applies to anything you have in mind. If I want to predict the failure of an aircraft, I need to understand the stresses that are induced by the loading environments that are applied to the aircraft. And that stress then can be compared to an intrinsic material property, which is strength. Like every material will have a strength. If I'm able to design a system where the stress is below the strength, then I can maybe have a good design that can survive the expected loading environments. Not the expected, but the maximum ones, right? We don't want to just design to the average load and suddenly the wind gust comes and breaks the whole thing apart, right? We don't want to do that. So we'll then, for that reason, introduce the idea of stress in this particular lecture. Um, and that's what I'm after here. So what is the outline of what I plan to present here is the very first three topics, is that you have external loads, you have boundary conditions, and you have to relate the external loads to the internal loads. That has to be the case. Somehow, if I want to know how this church is going to fail, I better tell you that somehow by relating that external load I'm applying to the system to whatever is going internally within the system. And if I can do that successfully, then I can design a system. And the idea of stress is really simple. Stresses are just internal force quantities that will resist the external loads that are applied. And those internal forces have to be in equilibrium with external loads applied. It has to be. Okay. So let's look at an example of two basic types of external forces that act on a body. On the left-hand side, what I'm showing is a body force. That vector G that I show is gravity, for example. But it could be a magnetic field that acts like a body force. So a body force is something that is acting at every point in the volume. And that body force acts in every point of the body in such a way that it produces a total force that's effective. And it can be applied, it can be acting in a particular direction. This particular body force tends to be a force per unit volume because that body force acts at every point in the body. And types of body forces include weight, inertia. And the other kind of load that you can apply to a body of material is a surface traction. In fact, that is the only load you can apply. A lot of times I hear a simplification, which is a very valid simplification, is I will apply a point load. For example, this 200 pounds looks like a point load, but the reality is there's not such a thing as a point load. Everything you can apply to a body of material, like a fuselage and this wing, has to be applied over surface area. Even this particular load here, which is supposed to represent the weight of a particular component hanging on the wing, even this load acts on a particular surface area. So every single load that you can apply to a body of material is a surface traction. It's a force per unit area. Example is an aircraft traveling is going to have drag, surface drag. And that drag is going to be tangential to the surface of the aircraft. In the case of lift, you're going to have a pressure acting perpendicular to the surface. And in this case, you can see this particular lift load apply to this wing, which causes the wing to bend and produce stress internally. It turns out that when you do the analysis, you'll find that the most critical location is here at this juncture, The exact location where I showed you in lecture, in the motivation lecture number 1, that the Boeing aircraft had experienced an issue, because that happens to be the highest, most critical location of interest. And so you could study this problem. There are boundary conditions that can be applied to a body of material, so it could be fixed, a part of the structure. One way to analyze this fuselage or this wing particularly could be to fix it on this end. If I fix it on this end, then I can study this wing by itself. But you have to remember that if you want to make sure that this joint doesn't fail, that this joint is also analyzed, even though your model is fixed to study that wing alone, as a beam, for example. This fuselage can be studied as a pressure vessel, also understanding that this external load can actually cause a lot of stresses in addition to the pressure that, in addition to the stress caused by the pressure inside the fuselage. Note, there are parts of the body of material that may not have any body forces, but there are parts that could be fixed. You can fix part of the surface, but you cannot apply a load in that surface also at the same time. So it's either one or the other can be applied in portion of that surface. What is going on? We want to look at the following. So the goal is to design a structural system such that the structure does not exhibit failure when it's subjected to these loads that we talked about, right? You have this boundary condition, maybe a boundary condition here, maybe a boundary condition here, maybe some loads here, some loads here, some loads here, some loads here. But if I were to do a cut plane here, I want to understand what is going on there, because my goal is to determine where in this complicated system, which looks like a potato, I give it to you, at some location in this structure, somewhere here, it must be the highest stress. And so for me to examine what that is, I can do a cut plane to understand what is going on. So given the boundary conditions, given the loads, external loads, something's going on inside the structure. And we need to determine those internal loads. Those internal loads are resisting these external loads. Okay? But to do that, for me to relate these external loads, for me to relate the external loads to what is going inside the body, I have to figure out how to relate that. I have to figure it out, how to relate external loads to internal loads. If I cannot do that, I have no chance of determining where the critical location is for predicting failure. The most critical location is that's critical to failure, I meant. So here's another example. I have a cantilever beam under self-weight loading. So say I have this beam and gravity alone bends it, say, right? If I section this beam somehow and I look inside, you'll see there's this stress, this loading that's preventing the structure from breaking. And these stresses or these forces are preventing, these forces are basically balancing the external forces. So for me to explain this concept a little bit better, we need to enter into the idea of stress and tractions. Let me dive into that, and then perhaps we can learn together what we're talking about here. So let me go back to what I talked about. I'll take this body material, make a cut right there, and look at what's going on inside. So I did that. I have this body of material with external loads applied, just like I said earlier. And then I'll take a little piece on that surface. After I do a cut, I look at a little piece, delta area, a small area, okay, which has a normal end. Okay, so that delta area has a normal end, and there's a traction force that's acting in that particular delta A. The delta F is acting on that particular little area there, okay? If I take the delta F divided by delta A, and I make delta A go to 0, I'm going to call this a traction. So that delta F divided by delta A, as the limit goes to delta A goes to 0, I'm going to define this as a traction. And that traction has units of the force per unit area. Okay. So that's what I define as a stress vector. So what you see here, that's the delta F I'm trying to look for that delta F divided by delta A. I'm trying to find this T, this traction inside the body material, because that's going to tell me where things will fail. These are the tractions here, which depend upon the location, right? This T here, which is a vector, is bolded for a reason. This vector here at every point of the body can vary, but there's a critical location where it could fail at. So the stress vector T that I'm talking about, which is a vector, has normal n, represents the force per unit area acting at a point on the surface A, that A there, where n, I use V here, but n is the unit normal to that area I'm looking at that point. And that traction vector T varies across that surface.
Is force?
So I will continue. So I want to clarify that stress vector or traction vector can be used interchangeably. And the vector of that force or this traction vector T can be pointed at a direction that's not necessarily aligned with n. It doesn't have to be aligned with n at all. Okay. And so that takes us to understanding a little bit better the idea of tractions and stresses. So let's examine that together. And what I'm going to do, I'm going to first discuss something called the free body diagram, which you should have covered that in a statics class or more elementary class. When I think of trying to determine where the system is going to fail, I want to understand how these tractions vary across every point in the material. And so what I want to do, I'm going to construct a little cube inside the volume of material. This body of material is subjected to a surface traction force. Like I said, you can apply an external force to the system. And that force that's applied to the system can be drag, lift, whatever you want to apply, pressure. And then this body of material is subjected to acceleration and also is subjected to body forces. What I can do is a free body diagram. I can extract a little cube from here and plot it here on the left-hand side. I'll go into what each of these means, but I'm going to take this cube of material and extract it out. I'm going to do a little surgery on this body of material and extract these cubes at every point in the body. There's infinite of them, but I'll select one of them, okay? And that cube of material will have 6 faces. I'll go into what these tiles mean in a second, but for now, bear with me. It has 6 faces. And what I'll discuss now is when I extract that cube, it looks like this. I extract this cube, okay? And that's the cube that's inside of the body. So I excised it out of the body material. And at each of these faces is going to have a normal. So for example, this face has a normal y. So the vector for that is 0, 1, 0, right? So is a vector that's going upwards. That's a normal to this surface. This surface here that you can see on the right-hand side has a one that goes in the x direction, and that vector is 1, 0, 0. That's a normal to this surface. So each of these has a normal, each of these faces. Right now, they align with the x, y, and z coordinate system. Each of these faces does. But like I said before, when I do a cut, like for example, I did a cut here, there's a traction that's acting on that delta area. So very similarly, I have a traction that's acting on that surface, and I have a traction acting on this surface, and I have a traction acting on this surface. That's what I have. Okay. And so again, what I did was I extracted this cube because what I'm interested is understanding the forces that develop internal to the body of material. because I know those internal forces, traction forces, are the ones that are reacting the external loads that you apply. In an airplane will be lift, drag, weight of the passengers, weight of the airplane, weight of the engine, and maybe the vibratory loads from the engine itself, the self-induced vibrations from that, the lateral loads that airplane experiences as it goes through turbulence, for example. Those are the external loads. The weight, the acceleration, those are the external loads. But where does it break? I need to understand where it's going to break by understanding what the stresses are. What are the stresses inside the body of material? And those are the force-like quantities that react those external loads. And so that's why the free body diagram, I cut this out, this little cube out, plotted it, and what you see here is these three traction forces shown in this picture. But if I took this traction force, for example, take the one on the right-hand side. This is very important for you to understand because it's going to make it more clear to you what we're looking at. So I have this traction force acting at an arbitrary orientation on that surface. If I took that traction force, Tx, which has components I, J, and K, if I were to decompose it into the X, Y, and Z direction, what I get are three components of that traction vector. And those three components are the stress components we're going to be talking about. So that traction acting on the X phase, that phase whose normal is aligned with the X direction, that traction that's arbitrary can be decomposed into these three directions. Every vector can be decomposed into the X and Y and Z component. You know that from pure geometry. And so if I decompose those into three different components as shown here, I'm going to call each of them as the stress components in that phase. For example, if I decompose the T, the traction force on the X direction, I will call that the sigma XX stress component. And it's sigma XX, there's an X missing here, I apologize. That sigma XX is because is in the X phase, in the X direction. That's what that means, XX. Let's look at when I decompose T into the one going in the Y direction. You can see here that I have sigma XY. I use tau here, but you can use sigma and tau interchangeably. Sigma XY or tau XY, that stress component is a stress that's acting on the X phase. You can see that's why there's an X there, but it's acting in the Y direction, okay? And then finally, in that same phase, I have another component, which is stress sigma xz or stress tau xz. There, you can use either convention. Tau is usually used for shear, but many books have also used it for this sigma. So every book is different. But the point here is that this stress component is sigma xz or tau xz, X phase, that first subscript, and Z tells you what direction, which is in the Z direction. You can see it's pointed along the Z direction. So again, you can see clearly that cut that cube out, but when I did that cut, that free body diagram, you can see there's tractions acting on each of these faces. There's six faces. You cannot see the other three faces because they're behind these three faces, but the same thing's happening in those faces. And the bottom line there is that this traction can be decomposed into these three directions, and these are the stress components. They're acting in that phase. The sigma xx is called the normal stress, and the ones tangential to that surface is called the shear stresses. So these two shear stresses are tangential to that surface whose normal is in the X direction. Let's now choose one more direction to make sure the idea has been reinforced. I have a traction vector acting on that top surface. This traction vector is acting on the Y surface, which is the reason I put a superscript Y, because this traction vector is not the same as this traction vector. They're different traction vectors. This traction vector is the one acting on this surface, and this traction vector is the one acting on this surface. I'll look at this traction vector, and what you find is that it can also be decomposed into the X, y, and z direction. The one decomposed in the y direction is called the sigma y. And you can see here, sigma y j hat, makes sense. J goes with y. You also have one that goes along the x direction, and that's stress yx. Is the y phase, makes sense. Y phase, the first subscript, and the x is the x direction. And you can see it has three components. I've covered two of them. The third component, which is the stress in the y phase, is acting in the z direction and is tangential to that surface. These two components, tau y is x, tau y is z, these two components are tangential to the surface, and those are the shear stresses. While the sigma yy is normal to the surface and is acting perpendicular to that surface. And you can see the three components here. And finally, but not least, is a traction whose normal, which is acting on a surface whose normal is along the z direction. And you can see there's also three components, 1, 2, and 3. Sigma zz is acting perpendicular to that surface, while the other two components, which the first subscript is z because it's acting on the z phase, and is y because it's in the y direction, and x in the x direction. These three components finally make up the traction z that you see here in the third line. This came from my book, this image, and this image also came from my book. Sigma zz, sigma xx, sigma yy, and sigma zz are the diagonal components here, while the off diagonal components can be seen here. You can see sigma y there, sigma z there, and then each of these have been transcribed here. And what you see here is that we have 9 components of stress, 9 components of stress that fully define a point in this body of material. Now I drew a cube, but this cube is infinitesimally small and it's a point. So this stress is a stress quantity that's at a particular point in the system and reacts the external loads that you apply to the system. And I'm after these stresses. This is what I'm after. I want to solve for these stresses, because if I know what the stresses are, I can tell you where is the most critical location, and then I can design for it. The normal stresses are usually in the diagonal, while the shear stresses are in the off diagonal. And so that right there covers the concept of stress, and is basically force per unit area. Excellent. So I want to repeat one more time. The stress components that are tangential to each of these surfaces are called the shear stresses, and they're the off diagonal terms in this matrix, while the diagonal terms are the ones that are normal to the cube, each of the faces of the cube. So the normal stresses are stresses that act so they're perpendicular to each of the faces of the cube, while the shear stresses, which are the off diagonal terms, these 3 terms and these 3 terms, are the ones that are tangential to each of the faces of the cube. So with that said, I'm going to move on here and discuss the following, because these tractions that I'm discussing, these stresses here, were basically discussed so that when I did the cut, these cuts were perfectly aligned with the X, Y, and Z. But what if I make a cut that's arbitrarily at a different plane? So that plane is not aligned with the X, Y, or Z. So I do like a cut that's diagonal, like some sort of triangle that connects these points here. Is going to be slanted. It's going to be a slanted surface. So what is going on there, and how you deal with that? So I can deal with that. What is a traction vector? That's a question at an arbitrary plane. So I have n hat. So I say I have a normal vector, which is a unit vector. This unit vector is arbitrarily oriented, and some orientation of a slanted surface. And this normal vector to that surface, which could be slanted, it's not like here where it's aligned, right? Each of these surfaces here is aligned with X, Y, and Z, but Now what I'm talking about is a slanted surface whose normal can be something else, right? Because right now, the normal vector that I'm looking at here for this one, for example, is 1, 0, 0. The one here is 0, 0, 1, this normal vector. This normal vector going up is 0, 1, 0, right? But what if it's slanted now, where each of these is non-zero, maybe? And so what is that traction vector at that arbitrary plane? So if the traction vector is this, defined like this and like this, we can simply find the projection of each of the traction vector onto this normal vector n. So if I take the dot product of this with n, what I get is sigma xx nx plus sigma xy ny plus sigma xz nz. And that traction vector is a traction vector that's along the x-axis, but acting on that arbitrary slanted surface whose normal is n. So all you have to do is a projection of two vectors to get it right. Let's look at the traction vector y. That traction vector y, and I'm looking at this one here, if I want to know what is going on in a slanted surface, I take that traction vector t and I dot that with a normal, with a surface whose normal n is this one here, and I do that dot product and I get this sigma y x nx plus sigma y y and y plus sigma y z and z. And finally, that third traction vector can also be projected on that surface whose normal is n, and it's slanted, right? It's slanted. So I get sigma zx nx plus sigma zy and y plus sigma zz and z. And so I can put that in matrix notation. You can see that here. So I have sigma xx here, sigma, I put tau here, but it's the same thing, sigma xy, sigma xz, right? So let's multiply. So how you multiply a matrix to a vector? So first row times column. So I have sigma xx times nx. You can see that there. Boom. Plus sigma xy times ny. You can see that there. Plus sigma xz times nz. You can see that there. And if you add those three components, you get tx. That's a traction vector. That's a traction component of the vector acting on that normal surface, on that surface, whose normal is n. Okay, and I can multiply a second row with that column there, and you will see that you get this as written here. And I can do that with a third row times that column, and you can see that you get exactly what I wrote here earlier with that dot product calculation. So why we don't do a quick test to see if this works out correctly, right? We should do a test to see if this works out correctly. So let's look to see if this works out. I want to find the components of, say, and say instead of a slanted surface, I have this surface I want to look at. So what is a normal to that surface? A normal to that surface n is 1, 0, 0. So this is 1, this is 0, and that's 0. So if you put 1, 0, and 0 here, and you did this multiplication the way I'm talking about, you'll get the traction components to be exactly this column vector here, and that's going to match what you see here. You're going to see that you get sigma xx, you're going to see that you get sigma zx, and then you're going to get sigma xy. So this is the calculation to get the tractions on an arbitrary slanted surface whose normal has a unit vector n. This is the right formula, and this formula is called the Cauchy's relationship. And I'll give an example coming up. Let's look at this example, which comes from my book. I have a state of stress in a cube, and these units are force per area, megapascals. And this stress field is at a given point of the structure, okay? It has normal stresses, sigma xx equals 40, sigma yy is 50, sigma zz is 40. And that's what I'm looking at here. And the off diagonal terms are shear stresses that we talked about, the off diagonal terms. And so that defines the stresses that we need to look at for this particular problem. So what I have here in this example is a state of stress that looks like this. That's what I have. And so since the stress field or the stress at a point is provided, they're asking us to find the tractions on this plane that's connected by A, B, and C. So let's look at what is going on first with the stress, state of stress. So sigma xx is 40. You can see that there is 40. And you can see that that makes total sense because this right here is 40. That's perpendicular to that surface AOB, right? Is acting on the X face and it's acting on the X direction. Then you have the sigma XY, which is also 40. And you can see it's acting downwards correctly. It's on the X face and it's acting on the Y direction. So that's also correct. And you may think, well, it's negative, it's in the negative direction, but I'm looking at the opposite face. And so that makes it positive because I'm looking at the opposite face. Sigma xz, however, in that same phase, like if the one, there's nothing going that way, it's zero. There's nothing going that way, zero. You can see that there is zero. Nothing's going on there. Now let's look at the triangle AOC, whose normal is in the Z direction. You can see there that the normal to that surface, so AO, we said AOC, right? So AOC is in the Z direction, right? The C face. So I'm actually looking at this face right here, the Z face. So sigma ZX, let's look at what I wrote there. The sigma ZX is zero. So that's why I didn't plot anything going that way. I didn't have anything to provide there. Sigma ZY, the Z face in the Y direction is 60. You can see going upwards like that. And it's minus 60 because I'm looking at the opposite face and that aligns with the Y direction. Sigma ZZ should be normal to that face and it's 40 and makes total sense because it's perpendicular to the face whose normal is in the Z direction. So you can see that this state of stress is correct, is accurate, and is working out per our discussion so far. So I also want to point out that this example is arbitrary. So the deltas here don't have they can be arbitrary. That can be any value you want. Let me cover a little bit better what was meant with the sign convention, right? So let me draw for you a square. So I'm going to look at this cube. I'm going to look at this face now, just that face, to make it easy for us to see everything in 2D. So this is the X direction, that's the Y direction. Sigma XX goes that way because it's in the X face in the X direction. If I look at the opposite face, the positive sign should be this way, sigma XX. And the reason is because this has to equilibrate that one. So if this is 40, in our example, this is 40, this has to be 40. Further, let's look at sigma XY. Sigma XY went this way. And we say that's positive 40. But I'm looking at the surface behind, which is behind, so you cannot see it very well. So that sigma XY is going downwards as a positive 40 because sigma XY in this phase has to equilibrate that one. by vertical equilibrium. So 40 and 40 in opposite directions are as shown here, and that's positive. And so that's why you see a 40. That's why you see a 40 here going downwards and a 40 going away from the normal surface, like that, in this diagram. Okay, so hopefully that sign convention is clear. So how do you go about this? The first step is to determine the normal vector n to surface of interest. In this case, the surface of interest is this one. Given the stress state in the other three surfaces, AOB, BOC, and COA, given the stress state that I showed you earlier, this one here, I want to know what the tractions are in that triangle ABC. That's what I'm interested in doing. Okay. And so to do that, I want to find a normal vector n first. And to do that, what you have to do is to calculate the area, for example, the area of AOB, which is the one that's perpendicular to the x direction, right? That area, for example, is what? 1/2 3 delta times delta. So that's 3/2 delta squared. And then you have to find the area for, say, BOC. That's 1/2 3 delta times 2 delta. 1/2 times the height and times the length. And that's what? That's 3 delta squared. Then you have to find the area of AOC. That's 1/2 delta times 2 delta, which is just delta squared. So that's what you see here. I found the vector that defines the normal, but you have to make sure it's a unit vector. So therefore you have to find the magnitude. So you have to find the magnitude and you do that by finding the magnitude like this, 3/2. And that's the magnitude of the area ABC. And that's what I calculated here. This gave me 7/2 delta squared, consistent to my book. So that's this number here. And each of these components is shown here one by one. And when you do the calculation, you find that the normal to that surface is given by this vector. So now that I found the vector n, and this example is straight out of my book, we are now ready to calculate the tractions that are acting on this surface here, the one here. That's what I'm trying to figure out, right? So I take the stress at that point, multiply by the n, the vector n that I found, and I find that the tractions acting on that surface is given by this vector. In other words, if I were to take a cube and the state of stress was defined by this stress state here, and that cube was taken out of, say, an airplane, right? That state of stress was taken from here, right? if I were to take a slanted surface and looked at it, okay, and I look at the tractions acting on that surface, if this was X, hold on, let's just say this X here, this is Y, and this is Z, for example, the traction component in the X direction goes that way. And it has a value of 360 divided by 7. The traction vector going in the Y direction, sorry, that was wrong, right? That's wrong. The X direction is going that way. This one right here is 360 divided by 7. The traction vector going in the Y direction is 300 divided by 7. And the traction vector going upwards is minus 280 divided by 7. Those are the tractions acting on that slanted surface. If I want to know what is the stress normal to this surface, what is the stress normal to this surface, I can take this traction that I calculated on that slanted surface and find the dot product with N. And that'll give me the stress that is perpendicular to the surface. So if I take this traction that's acting on that slanted surface and I dot it with N, that'll give me the stress that's perpendicular to the surface, okay? Which could be a useful quantity. So I'll try to draw on that slanted surface what you're asking me to do. I'll draw it in blue. So
Okay,
along the
thanks.
X direction, that's 360 divided by 7. So that's the X component of this traction vector. And then along the Y direction, you have 300 divided by 7. That's going along the Y direction. That's this one here. And I actually drew this incorrectly earlier. That's the Z direction that goes minus 280 divided by 7. It's the opposite direction. That's this one. Okay. There's a question about this. So this is usually used for matrix multiplication. This is a vector. That's a vector. But you will see books do it differently. So I don't want you to get stuck by those brackets. And so just make sure you don't get hung up by that. Okay. So what I want to do now, I want to relate the applied tractions to stresses inside the body. I can use that concept now because if I'm applying tractions on the body of material, these tractions, if I'm applying tractions on the surface of the material, I could relate it to stresses just adjacent to that surface. So I can take the cube there and look at that one, and I could use that to relate the tractions on the surface. If I know the normal to that surface, for example, I can also use that to relate it to the stresses just inside the body of material. I'll use that a little bit later. I won't use it yet, but just wanted to point that out, that this idea not only applies to a cube that's inside, but also a cube that's right here, right adjacent, where you could have a slanted surface to begin with. So we will use this concept. The main idea here is I would like you to review this formula here, which is called Cauchy's relationship. That's a part I would like you to review because that's an important calculation used for these problems. So another question that comes up is an interesting one. Is basically in which orientation are the stresses on each face normal to the surface? So there's no shear component. So there's a slanted surface, for example, there's a slanted surface that could construct such that the only stresses that exist are normal stresses. There's no shear stresses in them. And so to answer that question, there are ways we can look at that problem. We can actually look at that with the idea that we discussed. Okay. And I'll do that now. I'll explain how to determine that. So say I have a cube which has a stress field sigma, stress field has these values. And I'm repeating this right up so you can remember it. It can really stick to you here in a good way. That'll be a good thing. You know, we talked about this right here being the stress components normal to the surface of each side of the cube. We talked about it. While the remaining ones, which is this one and this one, are the off-diagonal terms which represent the shear stress components. So hopefully that idea is clear. What I'm asking right now is an interesting question that is asked quite often, which is, and is using failure criteria, and it comes a lot in the failure prediction of a lot of different materials, especially brittle materials. It's very useful there too. What I want to do, I want to determine the following. I want to determine if there is a slanted surface I can draw, some sort of slanted surface such that the only component of stress that exists is normal to this surface. So the stress component is normal to the slanted surface and there are no shear stresses tangential to the slanted surface. And hopefully that question is quite clear. And what I'll do then, I will then look at Cauchy's relationship again. And I know that tractions in a normal surface n, Txn, Tyn, Tzn is equal to sigma xx, etc. We've seen this already, and has a normal nx, ny, and nz. What I really want, I want these traction components on a slanted surface to really be equal to a stress times nx, ny, and z. That's what I really want, because if the traction is stress times a normal, then obviously that stress is aligned, that traction is aligned with this normal, right? Because if the normal to the surface is n, if I multiply by a scalar quantity stress, like some lambda, let me use lambda so we don't get confused, times lambda, then all I'm doing then, I'm just saying this traction is just normal to that surface. There's no other way. This traction here is normal to that surface if I just scale it up by some lambda, okay? That's the only way that can happen. And because that's the only way that can happen, this relationship has to be true. Okay. That stress I'm talking about is called a principal stress. Is a slanted surface at which only normal stresses to the slanted surface are acting. There's no tangential stresses. So stress at that particular point times the normal to the slanted surface, which I don't know what it is yet, has to be equal to some scalar quantity, which is actually a stress, a principal stress, times the normal vector. It has to be that way. So if I take that relationship, I can bring this to the left-hand side, so I get something like this: sigma xx minus lambda, sigma xy, sigma xz, and then I have sigma yy minus lambda, sigma yz, and then sigma zz minus lambda, sigma zy, sigma zx, sigma yx, has to be this way. If I bring the right-hand side to the left-hand side, it has to be that way. There's no other way, right? That's what you get when you do that calculation. If you notice, n, this vector normal n, cannot be 0. So that means the determinant has to be equal to 0 for this to be true. And so if I were to write these in 3 different equations, in my book, I show you that you get these 3 equations, and you can check that yourself. If I multiply this row that times that column, this row times this column, this row times that column, you get these 3 equations. And you can then calculate the determinant of this right here, the determinant of that. And when you do that, you get a cubic equation. And if you solve for the roots of that cubic equation, you actually get the 3 principal stresses. And those 3 principal stresses corresponds to 3 principal directions where only normal stresses are acting on that slanted surface. So there's 3 slanted surfaces where a normal force only acts on that surface. There's no tangential forces. To give an example from my book, I provide a stress state at a point, and that's this stress state at a point. And what I did there, I took 3 minus lambda, 1, 1, 1 minus lambda, 2, 1, 2 minus lambda. And I found this determinant and set equal to 0. When you set this determinant equal to 0, which I hope you can review how to find the determinants of a matrix, what you find is this cubic equation. And if you plug in this cubic equation into, say, for example, this website, wolframalpha.com, which it can solve equations, you actually get these 3 roots for that equation: 4, 1, and minus 2. You can then take each of the roots of the equation and back substitute it back into the fundamental systems we talked about. So for example, I have sigma equals 4. Then I'll go into my equation, this equation here, and plug in minus 4 here. When I do that, I'll get these 3 equations: 1, 2, and 3. And that will make sense. I can do it quick so you can see it. So 3 minus 4 is minus 1. 1, 1, 1. Minus 4. Sorry. 4, because lambda is 4, so that's minus 2, 1, 2, minus 4, because lambda, I found through Wolfram alpha that one of the roots is 4 from the cubic equation. Then based on that, I can then solve for each of the eigenvectors. I get 3 eigenvectors. I get, and one condition is that this needs to be a unit vector, by the way, n1 squared plus n2 squared plus n3 squared equals 1. I invite you to go ahead and show that for lambda equals 4, for example, you find that this is one of the vectors that corresponds to lambda equals 4. And you can do that by solving the system of equations and enforcing this equal to 1. If you do that, you'll find that. And then the same thing for lambda equals 1, you find that the second vector slanted surface. So all this is saying is that the slanted surface had a normal that looked like this. Okay. If the slanted surface normal was this one, then that particular slanted surface will only have one stress component that's perpendicular to the surface, and that's and will have a value of 4. That's what he's saying. Okay. And then for the second vector, normal vector, slanted surface, where that happens is this one. That's the second vector where that happens. And that is going to have a magnitude of 1. The stress component is going to be normal to that surface. Okay. And it's going to have a value magnitude 1 with this. And the slanted surface is defined by this vector. The third vector is this one. And that third vector is going to have a magnitude of stress. That vector is the normal vector to the surface as slanted. And in that particular slanted surface, it has a stress magnitude of -2. And that stress is perpendicular to that surface. That's what we're talking about here. Okay. And these are the principal stresses. And this is important in design to understand how to get these principal stresses. You can write a MATLAB code really quick, like this same example I showed you. Like this example I showed you here is in my booked example, like this example. I'm not covering this example here, but if you take the same earlier example and you took that stress of stress in MATLAB, you can actually enter these things. If you wrote this code here in MATLAB, it's going to produce the stresses it's going to produce all the results for you automatically. Obviously, in the exam, you're going to have to do parts of it by hand. And so you want to practice on how to do this. So what I invite you to do for extra credit, if you have my book, then you have the steps. But if you want to try it on your own, for 10 points extra credit, if you can turn it by Friday, show me that you can get by hand these answers and turn it in. And if you do it, you will get extra credit towards your homework. And then check it against what MATLAB gave you. So if you do that, you get 10 points. And so with that, I want to thank you for listening to today's lecture. What I covered in today's lecture is a concept of stress. Stress, in summary, is a quantity that is a force-like quantity that reacts to external loads that are applied to the system. And I showed you how the stresses can be related to a slanted surface. I also showed you how stresses can be calculated. Principal stresses can be calculated on an arbitrary slanted surface, and how to find that slanted surface and what the principal stress that corresponds to that slanted surface is. And that's very useful in the design of brittle materials and other materials of interest. I'm going to do one more example. Given the state of stress at a point is 0, 1, 1, 1, 0, 1, 1, 1, 0. So these are the diagonal components are normal stresses, while the off diagonal terms are shear stresses. And you notice here that everything is shear stresses here. This is what we call a state of pure shear. So I could then calculate, I want to find what are the principal stresses and at what inclination it occurs. Remember, this state of stress defines the stresses in a cube. Okay. I want to know if I were to rotate that cube or draw a slanted surface, at which slanted surface you have a stress that's only normal to that slanted surface. So principal stress is a stress at which only a normal stress acts on the slanted surface. So there's no shear stresses, which is weird because in this example, if I were to extract a cube, everything in this example, everything in this stress state is a state of pure shear. It's all pure shear. There's no off diagonal terms. There's no, I'm sorry, there's no diagonal terms. There's no normal stresses. But there is a slanted surface where there's actually a normal stress. So I need to then construct the eigenvalue problem. We call that the eigenvalue problem. And so I just take the diagonal components and subtract minus lambda. So I have 0 minus lambda, 1, 1. 1, 0 minus lambda, 1, 1, 1, 0 minus lambda. And I'll find this determinant. And finding the determinant of this should be fairly easy to do. You get a cubic equation again, a cubic equation. Sorry, you should set this equal to 0 first. Cubic equation results from here. And the roots of that equation is that you get lambda equals 2, minus 1, and minus 1. These are the principal stresses. And where does these principal stresses occur? That's the next step, right? So I'll take one, I'll just do one root. So I'll take 2 and plug it in here. So then I have 0 minus 2, 1, 1, 1, 0 minus 2, 1, 1, 1, 0 minus 2, and 1, and 2, and 3 equal to 0. So I get 3 equations. Now I get 3 equations, minus 2, and 1, plus n2 plus n3, 0, n1 minus 2 n2 plus n2 is 0, and then I get n1 plus n2 minus twice n3 equal to 0. And so when you look at this very quickly, if you impose n1 squared plus n2 squared plus n3 squared equals 1, and you use these 3 equations, I won't do it here. What you get is that the first principal stress is 1 over square root of 3i plus 1 over square root of 3j plus 1 over square root of 3k. And it is that normal surface where this maximum stress occurs, this principal stress occurs. So that corresponds to a stress of 2. That's when that happens. When my slanted surface looks like this one, then the stress is purely normal. And then I have to repeat the process for the next principal stresses and so forth to figure it out. With that, I want to thank you for listening to this particular example.